The goal is to do maximums and minimums in functions of more than one variable. So I want to define a local maximum, a local minimum, a global maximum, a global minimum. Best part, the definitions are exactly the same as they were in Calc 1. The point AB creates a local maximum if it's got a larger z value than all of the ones near it. Now, near, when we did maximums and minimums, meant that there was some interval. In Calc 1, we had a local maximum, and it was the highest thing in some little interval, right? But here, little intervals are disks. So in the x and y plane, I have this point, AB, and in a neighborhood around it. When I say this xy is near AB, I mean there's some little circle. And for all xy within this circle, it's the highest point. Again, I'm going to go back to the example we've used this whole damn time, my hat. And I create a local maximum just by putting my hat on. Right? Top of my head. But that literally means it's the highest point in some little neighborhood. The surface could go up and down and back and forth in all sorts of different ways. How does this change if I want a local minimum? Say again? Yes. The opposite where? Right, so the only thing that happens differently is here. So if I replace this word maximum with the word minimum, then I replace this inequality with this inequality. And I turn the hat over. Okay. I have an absolute maximum, an absolute minimum, means it's not just true for all xy near AB, it's true for all xy, period, in the whole domain of the function. So I have local maximums, local minimums, global maximum, global minimum, the same way I had them in Calc 1. Locally highest, overall highest, locally lowest, overall lowest. But how did we find maximums and minimums in Calc 1? And that was our critical point, our critical number, or critical value. On the graph, what did I see on the graph of f of x at that point? In terms of derivative. In terms of the derivative. Not necessarily across the x-axis. The derivative would be equal to 0. The derivative would cross the x-axis there. That's how I found this 3. But on the graph of f, What did the fact that f prime of 0 tell me about the graph? When the derivative is 0, what's it tell me about the picture of the graph? Aha! I have a horizontal tangent line. The thing is flat. Now, I knew that that was going to give me a local minimum, in this case, an absolute minimum, because I know that the shape of this graph is a parabola. And because it's a positive x squared, I know it opens up. So I know that whatever critical point we have will be a lowest point. Let's take this same idea and go from 2 dimensions to 3 dimensions. So instead of x and y, let's do x, y, and z. Back up here, I have a surface, right? If I have a highest point or a lowest point, I would like to be able to say the same thing I said up in Calc 1, and that was actually Fermat's theorem. If f of xy has a local extreme, a max or a min, and partial f with respect to x and partial f with respect to y exist at, I forgot to name the point, local extreme at P, A, B. Exist at P, then partial of f with respect to x evaluated at the point equals 0, and partial of f with respect to y at the point equals 0. I will have a horizontal tangent, but it won't be a horizontal tangent line. It will be a horizontal tangent plane. Yeah. Finishing school, right? So this means that when I have maximums and minimums, I can find them where the derivative is 0. But that wasn't always true in Calc 1. There was another option. What was our other option in Calc 1? It could be a maximum, it could be a minimum, or it's not an extreme at all. Remember, if we go to do, say, f of x equals x cubed, well, then the derivative is equal to 0 at x equals 0. But x cubed does not have a maximum nor a minimum at 0. What if we call this something else? Promise we gave it a name. It turns out to be an inflection point, but the inflection point measures changes in concavity. So we went from concave down to concave up, and this happens to be an inflection point because of that change in concavity, but we gave it another name as well. I drew my little person stick figure. It's a saddle point. Picture the horse, right? Get the head in front of you, it flattens out, that's where you sit, and then the tail keeps going down. Ah, it's a saddle point. And by the way, the change in concavity was how we figured out whether we had a maximum or a minimum, or neither. That was one of our tests. All right, I like this idea. Let's see if we can make it work. Here, just like we did with x squared, that quadratic that I did earlier, here's a quadratic in two variables. F of xy is x squared plus y squared minus 2x minus 6y plus 14. Do me a favor, open up your graphing, your web browser, go to Desmos, draw the picture of this thing. What's this look like? If I rearrange to complete the square, then this is x minus 1 squared plus y minus 3 squared plus 4. And yes, that's not just a parabola, a paraboloid. It's an upward opening parabola. Now, I will freely admit that I cheated. This is on page 960. There's our paraboloid. So let's find the critical points. If we've got them, they will occur where our first derivatives are 0. So let's take our first derivatives. Partial with respect to x. Partial with respect to y. So where my partial derivatives both are 0 turns out to be x equals 1 and y equals 3. And now, because I know the shape, I can say, perfect, this is an upward opening parabola. It is going to have a bottom. Our critical point is the bottom of this parabola. That's a local minimum. As a matter of fact, it's an absolute minimum, because I can look at the rest of the graph and say, oh, no, that work makes perfect sense. So not only do I know where the critical point is, I know what the minimum value is. The minimum value is 4. Plug in 1, 3, I get out 4. That's my lowest height. Questions? I would like you to do the same thing here. I'd like you to find the critical points and then figure out what kind of thing is going on. I'm sorry, say that again. Oh, let's check. Because my partial derivatives the only way those are 0 is when x is 0 and y is 0. I'm not disagreeing with that part, but you said this is a minimum. How do you know it's a minimum? I don't actually know that. I know that that's my critical point. You're absolutely right. The origin is my critical point, but I don't know what's happening at the origin. So let's graph this up. Draw me the picture. Say that again, Nora. It's both. What the frack do you mean it's both? What shape is this? Chapter 12, section 6. Aha. This shape's a hyperbolic paraboloid. And the hyperbolic paraboloid, the problem is that in one direction it goes up, in the other direction it goes down. In this case, our surface goes up in the x direction while going down in the y direction. Hold your hand out in front of you with your thumb up and your palm to one side. From your thumb to your forefinger, there's our upward opening piece in the x direction. From your palm to the back of your hand, there's our downward opening piece in the y direction. Page 961. Okay, this one is actually y squared minus x squared. This is turned 90 degrees. So just picture that, but turn it facing the other way. Wait a minute. Wait a minute. I don't even need to draw the little person on it. What shape do we call that? And it's a hyperbolic paraboloid, but we gave it the same name. That's a saddle. I mean, quite literally, that's the shape a saddle makes. Your legs go down on the side of the horse. Go under your butt, it goes up and down in the front and the back. Perfect. Okay, wait a second. This is neither a maximum nor a minimum. This is a saddle point. Okay, hang on a second. Let me go back to the ones where I have a maximum or I have a minimum. Mia, make the gesture you made with your hands about the saddle point. I have an upward opening parabola, I have a downward opening parabola. Yeah. But if I actually had a maximum and I looked at the x derivative, it would be going down. If I look at the y derivative, it would also be going down, right? Front to back and side to side. Go down between my eyebrows, and go down between my ears. If it was a minimum, then they would both be going up, right? In the x direction and the y direction. Wait a minute. I don't want to think about tangent lines. Tangent lines are flat. The tangent plane is flat. I want to think about the curvature, like we did back here. How did I know this was a minimum other than knowing that this was an upward opening parabola? It's on the second exam in Calc 1. Here's a function, find its maximums and minimums. What do? I do the second derivative. I could make a sign chart because I'll look to the left, I'll look to the right. But here in 3 variables, I don't know how to look to the left or the right. I have to look in front and back and left and right and up and all these other. I don't want to do that. But I look at the second derivative. So my second derivative test. Let me go back to Calc 1. F of x has a critical value at x equals c. F prime of c is 0. If f double prime of c is positive, then if f double prime of c is negative, then if f double prime of c equals 0, then. So back in chapter 4, section 3, I think, somewhere in there, middle of chapter 4, we've got a discussion about the second derivative test. What did we know? If my second derivative is positive, then my graph is concave up. And I wrote a little mnemonic device. How did I help you remember that? If my second derivative is positive, my graph is concave up. Second derivative is negative. My graph is concave down. And if my second derivative is 0, I don't have any concavity. I'm flat. Or I just don't know if it's concave or concave down. Now, if it's concave up, my horizontal tangent line must be at the bottom of that little concavity. We have a minimum. If it's concave down, it must be up at the top. We have a maximum. And if it's not concave there, I have a saddle point. Now, this is a fabulous idea because it means I can take my critical number and I can plug it into the second derivative. Oh, crap. My idea just went in my head. Problem. I don't have a second derivative. How many second derivatives do I have? I've got 4 second derivatives. Crap. Okay, wait a minute. What I need to know is which way those two parabolas go, right? If they both go up or both go down, I'll have a minimum or a maximum. But if one goes each way, then I'll have a saddle. Regardless of whether it's the left, right, going up and the front, back, going down, or the other way, that's a saddle. So I need to know how all 4 of those second derivatives work together. Now that sounds absolutely nuts until it turns out that there's a really nice way to put all those second derivatives together. However, in order to do this, I need all of my second derivatives to be continuous. I'm going to use that same near idea. Because I'm going to use this so often, I'm going to introduce a new term. I'm going to introduce DAB. D means disk. I want you to think of a disk whose center is AB. When I specify the radius, I'll put the radius as a subscript. I know that kind of looks like it should be a partial derivative or a directional derivative, but you'll notice that's not a vector. R is an actual number. So that's the disk of radius R centered at AB. So when I say near AB, I mean on some disk. If all the second derivatives are continuous near AB and its critical point, then what I'm going to do is I'm going to multiply my 4 derivatives together. Well, I'm going to multiply and subtract. Then set D equals. D here stands for discriminant. I'm going to discriminate between my 3 cases, just like I did up here. I only used the second derivative once, but my second derivative now is fxx of AB times fyy of AB minus fxy of AB times fyx of AB. Notice the mixed partial derivatives are together and the non-mixed partial derivatives are together. So I have xx and yy, and I have xy and yx. If D is bigger than 0, AB is an extreme. That means it's either a maximum or a minimum. I don't know which one, but it's either a maximum or a minimum. So how would I figure out which one? I just need to know which way one of the parabolas is going. Is one of the parabolas going up or is one of the parabolas going down? So pick one of your non-mixed second derivatives. We almost always use fxx. If fxx of AB is positive, then AB is a minimum. If fxx of AB is less than 0, then AB is a maximum. Hey, wait a minute. Positive means minimum, negative means maximum. That's the same smiley face and frowny face. So if there's more change this way than there is in the mixed ones, then we're going more together than we are separately. If there's more change in the mixed ones, then we're going to go in two different directions when we go in two different ways. If I go in X and then Y, I'll go down and then up. Well, that's going to be more negative behavior than positive behavior. If D is negative, then AB is a saddle point. Hey, wait a minute. I've missed an option. What's the option I've missed? If it equals 0, this test doesn't tell me. This is like the ratio test. I know what happened when the limit was less than 1. I know what happened when the limit was bigger than 1. When the limit was equal to 1, this test didn't tell me squat. If the discriminant is 0, this test does not give me any information. And then I'm going to have to read some other information out of the graph. I'm going to have to draw some pictures. I'm going to have to make some traces. I'm going to have to do some slicing to figure out what this picture looks like. I don't want to do that, so I'm hoping that I'll get stuck with cases where things work. This looks insane. But let's check it. We already know two functions. One of them has a minimum, one of them has a saddle point. Let's check. Our paraboloid, f of xy was x squared plus y squared minus 2x minus 6y plus 14. Our critical point was at what point? 1, 3. Now, those were our first derivatives. What are our second derivatives? What's fxx, fxy, fyx, and fyy? Say again. There are 4 things here. I need 4 numbers total. Well, 4 things total. So what's my discriminant? D here. If my second derivative test discriminant is positive, means I have an extreme. How do I know whether it's up or down? Jack?
Isn't it based off of fxx is positive or negative?
Yes. Since the second derivative there is positive, we are concave up. And that means we have a minimum, which matches what we got because we knew this was a paraboloid and it opened upward. So I can justify that without a picture. If I do the hyperbolic paraboloid, since that's a saddle, should get 0, 0. What are my second derivatives here? And d fxx fyy minus fxy fyx equals 2 times -2 minus 0 times 0. That's -4, less than 0. We have a saddle point. Please notice that when I wrote the second derivatives, under fx, I wrote xx, then xy. Under fy, I wrote yx, and then yy. The reason I did this is because I hate remembering this formula for D. This formula for the discriminant sucks. So I cheat. And I don't remember it this way. It's those 4 pieces, right? It's a determinant. AD minus BC, son of a... But the order matters. The first columns are the x derivatives first. The second columns are the y derivatives first. The first row are the x derivatives second. The second row are the y derivatives second. So your first derivative is by column, your second derivative is by row. But if I always remember it's xy and xy, that helps. XY and XY. And that's why I kept writing them in that order up there. So I could see 2 times -2, 0 times 0. Please note, we really don't need both of the mixed derivatives. Why? We really only need one, fyx or fxy. Whatever that guy's name is, they're the same, right? Clairaut's theorem tells me those are always the same. Some textbooks will actually write our formula for D as fxx fyy minus fxy squared for just that reason. I don't care which version you want to remember it by. This one, or this one, or this one, they're all equivalent. Questions?
If they were to be like 100 that, would it, like I'm blanking on the name of what the second way you showed us was, or what's that one called here?
This,
Yeah,
these are my second partials. Oh, you mean if I wrote them with the other notation?
yeah,
Yeah, if I write them with the other notation, it's messier, but it's the same idea. Because up here, we're doing x first. So this is the second derivative of x twice. This one is the second derivative with x first, then y. X first, then y. This one is the second derivative with y first, then x. And this is the second derivative y twice. That's the issue, is that the subscripts get read left to right. The D's get read right to left. Advantage. I said this only worked if the functions were continuous. If the functions are continuous, those two are going to be the same. So it really doesn't matter which one you do. You just have to do one of them and then put it in both spots. More questions? I'm sorry? Well, then I just have to have actually compute the z values, tell me which one's highest and which one's lowest. Absolute maximums and minimums globally means you first find all the local ones and then you compute all the z's. But notice that statement says globally. There was another way we did absolute maximums and minimums, which is going to take much longer than 7 minutes, which is why this entire lecture is split over 2 days. We're going to do more of this on Wednesday. Before I get to that, though, let me do one other example. I would like you to find all the critical points here and use the discriminant to tell me what they are. Well, use the discriminant, tell me what you get. Now, this problem is substantially more difficult than either of the ones we already did. And you see that right from doing the first derivatives. As soon as I do the first derivatives, what's fx? What's fy?
EX squared minus 3y squared,
And fx, fy?
negative 6xy.
Holy crap. My partial derivatives are not one variable equations this time, which means I need to set these equal to 0. Means I have to solve 2 equations in 2 variables. Yeah, that sucks. All right, wait a minute. If fx is equal to 0, then 3x squared minus 3y squared is equal to 0. What does that tell me?
X and Y.
Almost. It tells me that x squared is equal to y squared, right? Which means when I take square roots, I could get a plus or a minus on one side. Which means I could have lots of different critical values, as long as the x and the y have opposite signs on each other. But I also have this. If fy is 0, well, wait a minute. X squared equals y squared means either x is y or x is negative y. So let's use each of these cases separately. If x is equal to y, then up here, this becomes minus 6y squared equals 0. And if x is equal to negative y, I put that in here, and I get 6y squared equals 0. What's the only way that's going to happen? When y is 0. But if y is 0, then in either of these cases, x equals 0 also. So there's only one critical point, and that critical point is 0, 0. Great, wonderful, fabulous, I love it. But notice it was a lot harder to do the actual algebra. The calculus was easy, the algebra sucked. Now I need to use my discriminant. So I need my second derivatives. What's fxx, fxy, fyx, and fyy? Second derivative times fxx. 6x. fxy, negative 6y. fyx is also negative 6y. And fyy. So now I do my discriminant, and I get 6x times negative 6x minus negative 6y times negative 6y, which is minus 36x squared minus 36y squared. What happens when you put in our critical point? In other words, in spite of all of that, this test didn't tell me, and there's a very good reason for that. This surface is twisted 3 ways, not 2. I printed this one. This is our surface. X-axis, y-axis. Notice the problem. I've got an x cubed here, which means it goes down on this side and up on that side, right? Well, it should go this way. If x positive goes to my right, x cubed goes that way. But here, we're kind of going down in some directions and up in other directions, but they're not perpendicular to each other. They're in this threefold symmetry. This is still a saddle shape, but it's a saddle shape with a tail. Leg, leg, tail. Got 3 downs instead of 2 downs, right? This is a monkey saddle with a monkey's tail. I wish I was making it. That's the name they gave this shape. It's called a monkey saddle. Leg, leg, tail. 3 downs, 3 ups. That's why my partial derivative discriminant turned out to be 0, because in the x direction, I've got a flat spot. It's not concave up or concave down. It's a saddle in x, and then it's different things in not just the xy direction, but in these diagonal directions too. And that's what's messing this up. It's got a different kind of symmetry to it. We will use this shape again, but this is my canonical counterexample, why the second derivative test isn't enough. Every now and then we actually need to draw traces and other curves. More on this on Wednesday, and we'll look at absolute maximums and minimums as well. I will see you all then.